Hello students, welcome to the class of Thermodynamics. I am Dr. Mohammad Uzair and today we are going to discuss about the methods to increase the efficiency of the Rankine cycle. Last time we discussed about the actual cycle, the actual Rankine cycle, or basically we studied about the deviation of the actual cycle from the ideal cycle. So today we are basically going to discuss the methods to increase the efficiency of the Rankine cycle. So first of all, there is a question that why we are more concerned to increase the efficiency of the Rankine cycle. So the answer is normally when we are talking about the electricity power, so the steam power plants are responsible for the production of most electric power in the world. So if there is a small increase in the thermal efficiency, then it's mean you are going to produce more power, and then you are going to save the fuel as well, because when you are saying the efficiency increase, so it's mean you are getting more power and you are using less fuel. Therefore every effort is made to improve the efficiency of the cycle on which the steam power plants operate. So the basic idea behind all the modification to increase the thermal efficiency of the power cycle is the same. So what is the basic idea? Basic idea is to increase the average temperature at which the heat is transferred to the working fluid in the boiler, or decrease the average temperature at which the heat is rejected from the working fluid in the condenser. So this is the basic idea. Means if you are going to increase the average temperature at which the heat is transferred to the working fluid in the boiler, then there will be increase in the efficiency. Or if you are going to decrease the average temperature at which the heat is rejected from the working fluid in the condenser, again there will be increase in the efficiency. We will see these two terms in the next slides. So that is, the average fluid temperature should be as high as possible during heat addition and as low as possible during heat rejection process. So first of all, we are going to check that how we can increase the efficiency if we are going to decrease the condenser pressure. Here if you see the TS diagram, you can see the state number 1, 2, 3 and 4. You can see these states. These are the actual 1, 2, 3 and 4. This is the ideal Rankine cycle operating between these two pressure limits. As we know, the steam exists as a saturated mixture and the condenser at the saturation temperature corresponding to the pressure inside the condenser. So here if you have the pressure, you will get the saturation temperature here, and because we are basically in the condenser, we will have the vapor mixture region, so it's mean from 4 to 1 the temperature will be same. As we discussed in the last slide, that if we are going to decrease the average temperature of the condenser, then we can increase the efficiency. So let's suppose we are going to change the pressure, because the temperature is attached with the pressure. So if instead of stopping the turbine operation somewhere here, we are basically going to decrease the condenser pressure. Now this is the turbine exit now. So this is the turbine exit and this is the condenser entry. So therefore lowering the operating pressure of the condenser automatically lowers the temperature of the steam, and thus this temperature at which heat is rejected. Now what will be the benefit if we are going to decrease the condenser pressure? Okay, for the simplicity, I have chosen the turbine inlet, uh, like turbine inlet, same for both cases. So here we have the case number 1 where we have the pressure at somewhere at higher, like we have the higher pressure, and then we have another pressure line which is the lower pressure line. So the turbine inlet is same for both cases. So if I'm going to run the Rankine cycle on this cycle or this by using these processes, or if I'm going to operate the Rankine cycle with the help of like 3 then 4 dash instead of 4 and then 1 dash and then 2 dash and this one. So by doing this we will get this colored area. So you can see this one. So this is the this colored area on this diagram represent the increase in the net work output as a result of lowering the condenser pressure from P4 to P4 dash. So basically what is work output? Work output is this one, 3 to 4. So if I'm going to decrease the pressure, so we will get this one from here to here, from 4 to 4 dash, we will get some extra work output. So this is the extra work output. On the other hand, the heat input requirement also increases. Here in the starting one case, we had 1 to 2, but if we are moving with this line, so basically the heat input requirement, which was initially it was from like 2 to 3, now we have to add more heat from 2 dash to 2 because we have this cycle. So this much amount of heat is extra that you have to provide to the steam. We are getting some work here which is 4 to 4 dash, and we have to increase some heat input which is somewhere here, but this increase is very small compared with this gain. So gain is more, the increase the heat input is less. So thus the overall effect of the lowering this condenser pressure is an increase in the thermal efficiency of the cycle. Now, to take the advantage of the increased efficiencies at lower pressure, the condensers of the steam power plant really operate well below the atmospheric pressure. This one. So normally they are operated well below the atmospheric pressure. This doesn't present a major problem since the vapor pressure cycle operates in a closed loop. However, there is a lower limit on the condenser pressure that can be used. It cannot be lower than the saturation pressure corresponding to the temperature of the cooling medium. Normally what happens here around the condenser, because a condenser is a type of heat exchanger, so around the condenser we have the cooling water that is circulating through either lake or river, and the water is basically picking the heat that is rejected by this condenser. So there is lower limit on the condenser pressure that can be used. So you cannot decrease the pressure than the saturation pressure corresponding to the temperature of the cooling medium. Let's suppose if I'm saying that we have the condenser that is to be cooled by a nearby lake or river or something else, and we have the temperature of 15 degree. 15 degree for the temperature of the lake water. So when the lake water is circulating over this condenser tube, normally we have to provide at least 10 degree delta T for a good heat transfer. So it's mean we will have the condenser temperature around like 25 degrees Celsius. So let's suppose if we have the lake water at 15 degree, so in order to allow the heat transfer, there should be high temperature in the condenser. So let's suppose we have the 10 degree increase, so we will have the condenser temperature around 25 degrees Celsius. So we have the condenser which must be above like 25 degrees Celsius. So thus the condenser pressure must be above the saturation pressure at 25. So normally if I'm going to check the saturation temperature around 25 degrees Celsius, so it will be around like 3.2 kilopascal. That means you can decrease up to 3.2 kilopascal. So basically you have to check the outside water temperature. If it's like 15 degree or 20 degree, then use the condenser temperature around 10 degree above the lake water temperature, and check what is the saturation pressure against that temperature. So that will be the lower limit that you can achieve in by lowering your condenser pressure. So you cannot decrease the pressure below than the saturation pressure. So here, when we are going to decrease the condenser pressure, there will be no side effect, but there is a chance that it creates the possibility of air leakage into the condenser. There is a rare chance, because we are going to decrease the pressure, then the atmospheric pressure, so then there's a chance that the air will flow from outside to inside. The air will flow from outside atmosphere to the inside of condenser, so there is a basically air leakage into the condenser. More importantly, it increases the moisture content of the steam at the final stage of turbine. So you can see here, if I'm going to decrease the pressure, so the 4 dash is somewhere in the vapor liquid mixture. Here we have the higher quality, or like it's very close to the vapor line, saturated vapor line, but here we will get the lower quality of the steam, that is the outlet of the turbine. So when you will get the low quality, or you will get the moisture content of the steam at the final stage of the turbine. So this can create the erosion or corrosion on the blades of the turbine, that can damage the turbine as well. So normally it is recommended that we can, like at the end of the turbine, we should have at least 90% of the quality. So here we have already discussed this slide with the previous diagram. So it's already we have already discussed about these things. But if you see the last line, the presence of the large quantities of the moisture is highly undesirable in turbines, because it decreases the turbine efficiency and erodes the turbine blades, because we have the 4 dash here. So there is a chance that we can decrease the pressure, as well as we can do something else to shift this point to somewhere here. So for this one, we have to do another thing, which is called the superheating the steam to high temperatures. Means you are going to increase the average temperature, the high temperature. So the average temperature at which the heat is transferred to the steam can be increased without increasing the boiler pressure by superheating the steam to high temperatures. So last time it was somewhere here. Now we are going to increase the temperature. So when we are going to increase the temperature, and then this is the turbine inlet. So when there's an expansion in the turbine, so you can see the 4 dash is somewhere here, which is close to the vapor, the saturated vapor line. So it's been again the water or the moisture content at the last stages of the turbine will be less, or the quality will be higher. So the chance of the erosion and corrosion is reduced here due to this superheating. So superheating the steam to the high temperature has another very desirable effect. This is basically the same one. Like it decreases the moisture contents of the steam at the turbine exit. So when it's going to decrease the moisture content, so it's mean you will get the high quality here at this point. Now by doing this superheating, so you can see we have this colored area, this one. So basically the colored area on this diagram represent the increase in the net work. This is the increase in the net work. The total area under the process curve of this 3 and 3 dash, sorry, this one 3 and 3 dash, this one represent the increase in the heat input. So we have the heat input and we have the W net. So thus both the net work and heat input increases as a result of the superheating to the steam to a high temperature. The overall effect is an increase in the thermal efficiency. However, since the average temperature at which heat is added increases, so normally you will get the higher efficiency here. Now there is a question: what is the maximum limit to superheat the steam? Because if we are getting the increase in the efficiency, then we can increase up to any limit. So the answer is the temperature to which the steam can be superheated is limited. Why? Because we have the boiler and you are going to increase the temperature inside the boiler at the constant pressure, and boiler is made of something from any metal or ceramic or composite, so you are basically going to use the material. So what happens when you are going to increase the pressure, when you're going to increase the temperature at the constant pressure, so we will have a metallurgical consideration. Presently the highest steam temperature allowed at the turbine inlet is about 620 degrees Celsius. So any increase in this value depends on improving the present material or finding new ones that can withstand the high temperature. Because at the high temperature, the material there's a chance that the material will start melt. There is a there's a chance that the material will break, or there will be some leakage, or there will be some cracks. So there is a limit to increase the steam temperature, or the limit to superheat the steam. But again, in this case, we will get the higher efficiency. Now there is one more way to increase the efficiency, and this time we are going to increase the efficiency by increasing the boiler pressure. So you can see we have the line. We have two different lines. One is like 1, 2, 3, and 4. Which is this one. So you can see 1, 2, and 3, and 4. But now we are going to increase the boiler efficient. Boiler pressure. So if you're going to increase the boiler pressure, so you will get this line, because the higher pressure, and we have the maximum T max. So we have the limit for the maximum temperature. So at the high pressure, you will get a line like this one, and then we will have like this one. So by doing this one, you are basically you are going to increase the temperature at which boiling take place. Because if you're going to increase the pressure, so T saturation will change, and ultimately there is a rise in the temperature at which boiling take place. So thus in turn rises the average temperature at which heat is transferred to the steam, and thus rises and thus basically increase the thermal efficiency of the cycle. So this is another way to increase the efficiency. So here again, the effect of increasing the boiler pressure on the performance of the vapor power cycle is given in this picture. So we have now here we have two different color line. One is portion. We have this portion color portion, and we have the portion like this one. So here, if you see, we have this one. So it's mean basically we will get a decrease in the W net. So we have the decrease in the W net. For these two cases, 3 to 4 and 3 dash to 4 dash, we are assuming that we have the same turbine inlet. So what will happen? We will get the decrease in the W net, and here you can see by increasing the pressure, boiler pressure, you will get the higher moisture content at the outlet of the turbine. Again, it's a dangerous thing, because when you are going to increase the pressure, the turbine will experience the moisture content in the last stages of the turbine. So we have the 4, and this is 4 dash. So this is due to the increase in the pressure. So we are getting the decrease in the W net, as well as if you see the this color line and color portion, we are basically getting the increase in the W net as well. So we have the decrease in the W net due to the change of this turbine line from right to left. But when we are going to change the pressure line, we are moving upward, so we are getting some increase in the W net. And this increase in the W net is more than the decrease in the W net. Also, we will get some increase in the heat transfer or the heat input. So you can see here we are basically using this 2 to 2 dash. So pump work is also increased, and we will have this amount of heat here. Ultimately, what will happen, there will be increase in the efficiency. We will get the increase in the efficiency. Now, when we are talking about the increasing the boiler pressure, so in the start, when we had the Rankine cycle, like let's suppose if we're talking about the 1920s. At that time, the boiler pressure was around 2.5 or 2.7 megapascal, and then with the advancement now in the recently we have increased the boiler pressure up to around 30 megapascal. So basically, by increasing the pressure, we are getting more and more power, or we are going to increase the efficiency here. There is another thing that there are some modern steam power plants that operates on the supercritical pressure, which is like pressure which is more than 22.06 megapascal. So you know about the critical point. So they are the turbines or the Rankine cycle that are operating above the supercritical pressure, and they have the thermal efficiencies of around 40% for fossil fuels and around like 34-35% for the nuclear plants. uh, Normally we are using these type of plants where we are using the pressure below than the supercritical one. So we have three different ways to increase the efficiency. We had the efficiency increased by decreasing the condenser pressure. Then we checked the increase in the efficiency by superheating, and then we have the third method to increase the efficiency by increasing the boiler pressure. So here we have some questions. Let's suppose we have the simple ideal Rankine cycle with fixed turbine inlet conditions. So turbine inlet conditions is same. So what is the effect of the lowering of the condenser pressure on these things? So if we are going to decrease the condenser pressure, so what will happen? The pump work input will increase, decrease, or remains constant. And same way we have to check all this stuff. So it's better to draw the TS diagram first. So this is the TS diagram for this cycle when we are going to decrease the condenser pressure. So we have the cycle and the ideal one, which is 1, 2, 3, 4, and then we have decreased the condenser pressure, so we will get the 4 dash and 1 dash and 2 dash. So here when we are talking about the pump work input, so in the case of pump work input, you can see here we had 1 to 2. Previously it was 1 to 2. Okay, one thing, we have the fixed turbine inlet, so point number 3 is same for both cases. So we had the 1 to 2, and now we have 1 dash to 2 dash. So it's mean we will get the higher or increase in the pump work input. So you can see we have the increase in the pump work input because we have the larger line here. It was like shorter line here, and then when you're going to decrease the pressure, you will get the higher line here. What about the turbine work output? So in the previous case, when we were using the high pressure, we had 3 to 4. By decreasing the condenser pressure, we have 3 to 4 dash. So ultimately, we have the increase in the turbine work output. So from the 4 to 4 dash, we have basically increase in the work output. What about the heat supply? Heat supply was from 2 to 3, and now we have 2 dash to 3. So it's been 2 dash to 2, there is an increase. So basically heat supplied is also increases. What about the heat rejected? Previously it was from 4 to 1, and now we have 4 dash to 1 dash. It was 4 to 1, and now we have the 4 dash to 1 dash. Here we have something very special to remember. The heat rejected will decrease. It will decrease. How? Because at lower pressure you will get the lower H values. So H4 and H4 dash both have the different values. So H4 is a higher value, and H4 dash H4, and the enthalpy at 4 dash is lower. So there's already amount of heat is the amount of energy is already transferred in term of energy. So here you will get H4 dash, which is lower than the H4. Again H1 dash is again lower value. So this one here, the heat rejected will be decreases. So there is decrease in the heat rejected. What about the cycle efficiency? Cycle efficiency is going to increase because this is the method to increase the efficiency. So cycle efficiency will increases. Moisture content at the turbine exit, yes, of course it's going to increase. Firstly it was somewhere here, now it's somewhere here, so it's increased now. So here input, the pump work input was increased, turbine work output was increased, heat supplied was increased, cycle efficiency was increased, and moisture content is also increased. So one thing which is heat rejected, which is going to decrease here. So this is the answer. The heat rejected decreases while everything else increases when we have the Rankine cycle, and we are going to check the effect of lowering the condenser pressure. Now we have another question. If you see, we have the same question. Consider a simple ideal Rankine cycle with fixed turbine inlet and condenser pressure. Now the condenser pressure is fixed. What is the effect of the increasing boiler pressure on? Now we have to increase the boiler pressure, and we have to check the effect on all this stuff, which is the same as we had in the previous question. So first I'm going to draw a TS diagram, which is like this one. So here we have the increase in the condenser pressure. Oh, sorry, the increase in the boiler pressure. So we have the increase in the boiler pressure like this. So here, if you see, we have 1, then 2, 3, and 4. This is the original process, or original Rankine cycle, and then we have 1, 2 dash, 3 dash, and 4 dash. This is the modified Rankine cycle when we have increased the boiler pressure. Now we have to check the effect of the pump work input. So here you can see, initially it was 1 to 2, and now we have 2 to 2 dash. So basically, sorry, 1 to 2 dash. So basically there is an increase from 2 to 2 dash. So we have the increased pump work input. The same way the turbine work output will be increased. So this is the turbine work output. So it's going to increase. The heat supplied is again increased because at higher pressure you will get the higher values. Heat rejected, again it's going to decrease. So we have the heat rejected from here to here, and now for this case we have the heat rejected from this point to this point. So this value is less than compared with this one. So because there is this one, which is less amount of heat transfer. Cycle efficiency is of course going to increase, and moisture content is also going to increase at the turbine exit. So again, like previous question, for this one heat rejected decreases and everything else is going are going to increase. So everything is going to increase and heat rejected is going to decrease for this cycle as well. Now there's another problem, which is like this one. Consider simple ideal Rankine cycle with fixed boiler and condenser pressure. So in this case, we have to check what is the effect of the superheating the steam to the high temperature on these parameters. So like the previous question, first of all you have to draw the TS diagram. So the TS diagram is like this one. We have the TS diagram, we have the initial cycle, which comprises of the process from 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And when you're going to superheat the steam, so you will get 1 to 2, then 2 to 3 dash, and then 3 dash to 4 dash, and then 4 dash to 1. So here when we are going to check the pump work input, so you can see there is no effect on the pump work input. So pump work input will remains the same. So there is no effect on the pump work input. Turbine work output. So you can see we have the larger work output. So turbine work output is going to increase. So work output is basically increased when you are going to superheat the steam. Again, the heat supplied previously it was from 2 to 3. Now it's from 2 to 3 dash with superheating. So it's mean basically you are going to increase from 3 to 3 dash. So the heat supplied to this water is basically increased. What about the heat rejected? Last time it was 4 to 1 when I said that the heat is going to decrease, but now we have shifted from 4 to 4 dash. So basically you have increased the heat rejection. So heat rejection is going to increase. Cycle efficiency, of course, there is an increase in the cycle efficiency, and the moisture content at the turbine exit are going to decrease. Initially it was at 0.4 and now we have a new point which is 4 dash. So the moisture contents are going to decrease when we are using the superheating process. So here if you see the answer, so the pump work remains the same, the moisture content decreases, everything else increases. So as we know there is no effect on the pump work, so it's almost constant, so remains the same. And the moisture content decreases from here to here, so moisture content decreases, everything else increases. So you can see work output is increased, the q in is increased, the heat rejection is basically increased, even the efficiency is going to increase for this case. So in today's class we have basically checked the different ways to increase the efficiency of the Rankine cycle. Firstly, we decrease the condenser pressure and check the effect on the different parameters, and the overall effect was the increase in the efficiency. And then we checked about the superheating process, and again efficiency was increased. And in the last basically we checked about the increased in the boiler pressure, and in all these three cases the efficiency was increased. So normally what we do, as we already discussed in the class, that there is a limit to decrease the condenser pressure, which is around the saturation pressure of the condenser temperature. For the superheating we have limit that we go up to around like 620 or 630 due to the involvement of the material, because there is a material that can be ruptured or that can be melt by increasing the temperature. And when we are talking about the boiler pressure, again recently, like up to today, we have the boiler pressure, the operating boiler pressure up to 30 megapascal. So we can increase up to 30 megapascal, which is like above the supercritical pressure. But still, we are using within this subcritical region, and we perform the complete process, and we get the power from the Rankine cycle. So for today's class, I think it's enough. In the next class, we will try to solve the numerical problem for the same case. That we will check the effect of these if we are going to decrease the pressure or increase the boiler pressure or superheating, then what will be the effect on the efficiency. So there is a question which is given in the book, especially a solved example, which is I think 10-3. It is a good example, and we will discuss that example in the next class. So thank you. This one.